autonomous differential equation, we have to sketch y in the y prime plane. Yeah?
Oh wait, so we're not integrating.
No, we don't have to solve it. We need to sketch it. That's what we do to figure out a phase line diagram.
Right.
Yeah. So I'm sure you know how to sketch a parabola, yeah? Because in the y prime y plane, this looks like a parabola. It's like saying y equals x squared minus x minus 6 in a way. No? So, you know, we could factor it out to figure out what the intercepts are. So 3 and minus 2. No? So if we were to sketch this, we have the minus 2 and the 3, right? And this is your y prime here on the y-axis, and y goes on the x-axis. Okay. Right. And you remember you could figure out what the maximum or the minimum height of this parabola is from the derivative, or you could do minus b over 2a. So that would be minus 1 over 2, so half. And then plug it in, so this would be 1/4 minus half minus 6. Right? So that's minus 6.5. So minus 6 1/4. So half minus 6 1/4. So let's just say somewhere here. So then the graph will look something like this. Going through this point, of course. Okay. So this is the sketch of the differential equation in the y plane. And we need to draw a phase line diagram. So the line diagram would basically state what the equilibrium points are and what's happening in their neighborhood.
Yeah.
So we can figure out, so what are our equilibrium points here? The zeros, where the derivative is 0,
yeah,
where there's no change. When there's no change.
So
that happens at 3 and at -2. So these are in pink the equilibrium points. Yeah? So this is happening at 3 and at -2. And now we're going to go in the vicinity of these equilibrium points and see whether they are stable, half stable, or unstable. Yeah? And you remember how to do that?
Yeah, if it's increasing, well, the derivative is increasing after, then they're unstable, and if it's decreasing, they're stable.
Yeah. Right?
No, wait, if it, yeah, if it decreases, then it's stable.
Yeah. So let's go ahead and do that then. You want to mark them there and show me what you get? So technically on the -2, before the -2, it's positive, right? Um, it's it's slowing down. So that means here it's coming towards it.
Yeah, it decreases.
And it's also decreasing below it, so it's coming also towards it. So -2 looks to be a stable equilibrium point.
Right.
Is a stable equilibrium point. Okay. Whereas on the 3,
It's less than 0 on the left side, but then it increases.
right, so on the left side, the slope is positive, whereas negative, yeah?
Yeah, the derivative is negative. So the change is negative on the left side. And,
right.
And on the right side, though, it's positive, so it's half stable.
No, because doesn't it keep being positive on the right side of the graph? So that means it's going away from it. Because the slope, which is dy over dx, which is what this green graph represents, is the change.
Yeah.
It keeps on becoming larger. So that means it's going away from the point, and therefore y equals 3 is an unstable equilibrium point. That's an unstable equilibrium point. Right? And then he asks in the question to state the long-term behavior for all the initial conditions. So the long-term behavior, since one is stable, the other is
half stable though, because it's the derivative is negative. Oh no, wait. Oh yeah.
So the long-term behavior would be what? Since you are diverging away from 3 and going towards -2, so the long-term behavior is away from 3. So if, let's say, -2 is here and 3 is here, you are going away from 3, right? And you are approaching 2. So that's kind of the long-term behavior.
All right, yeah, I got it.
Sort of thing. You get it?
Yeah.
So this is the 3, and this guy here is the -2. That has to do with the stability.